We can also use the method of superposition to determine a shear force diagram for a frame subjected to multiple loads. So here we superimpose two cases with the loads applied separately. And for the first case, by a horizontal equilibrium of forces, we have 1 kN acting at the pin, and we know there's a vertical reaction at the pin, which I'll assume is acting downwards, and a vertical reaction at the roller, which I'll assume is acting upwards. Because this point load is causing tension in this column and compression in this one. And if we take a sum of moments about A, with anti-clockwise being positive, we have By by the moment arm of 3 meters minus 1 kN by the moment arm of 2 meters is equal to 0. And therefore By is 0.67 kN. And by vertical equilibrium of forces, Ay is also 0.67 kN, but acting downwards. And now if we cut the column, we can see that the shear force is constant at 1 kN. Now on the other side, if we take a free body off the right column, we have the reaction By acting on that column. And by vertical equilibrium, we must have an equal and opposite force acting on the top. And therefore by Newton's third law, we have an equal and opposite force acting on a beam of 0.67 kN. And now if we cut the beam from right to left, and therefore the shear force is negative and constant across that beam at minus 0.67 kN. And if we cut this column, the shear force in the column is 0, because there's no horizontal reaction at the roller. Now for the second case, you can also find the reactions for the pin and the roller by taking equilibrium of moments, for example, about B, with anti-clockwise being positive, we have minus Ay by the moment arm plus 2 kN by a moment arm of 2 meters. And that's equal to 0. So Ay is 1.33 kilonewtons. And by vertical equilibrium of forces, with upwards being positive, we have Ay plus By minus 2 kilonewtons is 0. So By is 0.67 kilonewtons. And by the same argument here, by Newton's third law, we'd have an equal and opposite force to that in the column acting on the beam. So that would be 1.33 kilonewtons. And this causes a jump in the shear force diagram of 1.33 kilonewtons. And then you have a jump due to the point load of 2 kilonewtons. So the shear force is minus 0.67 kilonewtons in the beam. And we can see that this is also equal in magnitude to the reaction By at this end. Now if you cut both columns, there's no horizontal reactions, so the shear force in the columns is 0. And now we can superimpose both cases. So we have the shear force in the beam of 1.33 kilonewtons minus 0.67 gives 0.66 kilonewtons. And here we have minus 0.67 minus 0.67 gives minus 1.34 kilonewtons. So you can see it's equal to that jump. And now in the left column, we have 1 kilonewton plus 0 gives a shear force of 1 kilonewton in the left column. That's constant. And in the right column we have 0 plus 0, so the shear force in this column on the right is 0. Please subscribe, like and comment to help me reach more students.